Hello, we are on 1.05 Algebra 2 notes today, and we're going to be talking about more of the radicals that we started last class. We're going to continue today. So we're going to go through a couple rules and then do some examples of each to start out with. So the first rule is that you cannot leave a fraction under a radical. Okay, so that's the first rule. So let's look at some examples of what I mean by this. So 9x to the 12th power over 49y to the 36th power. And I'm going to take the square root of that whole thing. So I can't leave a fraction underneath that entire radical. So what you're going to do is we're going to break it up into the square root of the numerator over the square root of the denominator. So the square root of 49y to the 36th power. Now we're just going to simplify everything as much as possible. So the numerator, we've got 9, that's a perfect square. The square root of 9 is 3. And then remember, any even exponents are perfect squares. So 12 is an even number. It's divisible by 2. So the square root, to find the square root of an exponent, you just divide it by 2. So we would take 3x to the 6th. The bottom, 49 is a perfect square, and again, we have an even exponent of 36. So we'll take the square root of 49 is 7, and divide 36 by 2, which gives us 18. And then just double check that you can't reduce anything. So 3 over 7 can't be reduced, x and y can't be reduced. So we're done with number 1. 7y to the 16th over 64y to the 8th, the square root of that entire fraction. Okay, so good idea to pause here. Try this one on your own, a little bit harder because there's a couple more steps at the end. See if you can do them and then check back and I'll go through it. All right, so first, anytime you're given the fraction, you're going to break it up into the numerator and the denominator. And this one, we have the numerator here is not a perfect square. So I'm going to break that up into my 2 radicals. So my 2 radicals, meaning the first one's all my perfect squares, and the second one is all the non-perfect squares. So 7 does not have a perfect square I can take out of it, so I'm going to put it in the non-perfect square radical. Y to the 16th is already a perfect square, so that's going to stay right here. Just be careful not to take the square root of it, but when you're putting it under the radical, you're just going to leave it as is for now, then take the square root in the next step. And for our denominator, the square root of 64 is 8, and the square root of y to the 8th is an even exponent, would be y to the 4th. So now let's simplify that numerator. So I've got the square root of y to the 16th power, 16 divided by 2, since I'm taking the square root, is 8, and the square root of 7 will stay in that radical, over 8 times y to the 4th. Now here, I can't reduce my 8 and my rad 7 since one's under a radical and one's not, but I do have y to the 8th and y to the 4th that can be reduced. So when I have the same variable on the top and the bottom, I ask myself, where do I have more? And my answer would be the top. How many more do I have? And I have 4 more. So that tells me that I'm going to keep a y to the 4th on the top because I have 4 more y's on the top than I do on the bottom. And that's as far as we can take that one because there's nothing we can break down from our radical any further. The y to the 4th is reduced as much as possible, so everything's simplified as much as possible. Actually, we're going to do our next rule now. So the next rule is that you can't leave a radical in the denominator. So hopefully you remember doing this in algebra. If not, we'll go over it again. So we call this rationalizing your denominator. So we'll start with 7 over 8y to the 3rd, square root of that whole thing. So we're still using the same first rule where we have the square root of a fraction. We can't leave a fraction underneath a radical. So we're going to break it up into the square root of the numerator over the square root of the denominator. Now, before we get rid of this, you have two options. You can get rid of it now, or you can put it into simplest radical form. I like to be in the habit of putting it into simplest radical form first so that I don't have really large numbers to simplify afterwards. So to do that, I'm going to set up my two radicals, take my largest perfect square from 8, which is 4 times 2, and then y to the third, I want to take out my largest perfect square there, so it's the largest even number before 3, which is 2. And then y to the second times y to the first gives me y to the third. Now I have the square root of 7 over the square root of 4y squared, which is 2y times the square root of 2y. So the problem now is that I have a square root in the denominator and I'm not allowed to leave it in the denominator. So what I do to rationalize it is I take whatever the square root is in the denominator, and this only works if it's being multiplied by something else, not if it's added or subtracted. And I'm going to multiply the bottom by rad 2y. Whatever I do to the bottom, I'm going to do to the top. So I'm going to make this note in green here. So this is called rationalizing the denominator. So to rationalize, you multiply the numerator and the denominator by whatever radical is in the denominator. Okay, so now that gives us, I'm going to actually go down here now. So I've got rad 7 times rad 2y, and what we talked about last class, you can multiply underneath the radical, so that gives me radical 14y. Rad 2y times rad 2y is just 2y. Whenever you multiply a radical by itself, you're left with whatever's under the radical. So I have 2y times 2y, which would give me 4y squared. So I have the square root of 14y over 4y squared. The top is in simplest radical form. There's nothing to reduce the bottom with, so we are done with number 3. Number 4. 4b times the square root of 3 over a times the square root of 6a to the second. So if you're feeling comfortable now, you might want to pause here and give this one a try, but I'll still go through it as well if you need me to. All right, first thing I like to do is, we don't need to break this one up, so I want to just make sure everything's in simplest radical form. So 3 is up on the top here, and the bottom, 6, I can't break that down any further, so I'm going to keep that in the second radical. A squared is a perfect square, so I'm going to put that one in the first. Still have 4b rad 3 on top, and then square root of a squared is a, so I have a times a gives me a squared times the square root of 6. Now the problem with this is that I have a radical in the denominator, and I'm not allowed to have a radical in the denominator. So I multiply the denominator and the numerator by whatever radical I need to get rid of in that denominator. Now I can combine some things in the top here. So I have rad 3 times rad 6 will give me rad 18. And in the denominator, rad 6 times rad 6 is 6. So I'm left with 6a squared. Not quite done yet on this one because I have rad 18, which I can break down. So I can do 4b times the square root of 9 times the square root of 2, largest perfect square, is 9 taken out of 18. And then I have 6a squared still in the denominator. The square root of 9 is 3, so if I multiply across the top, I get 4 times b times 3 times rad 2, so that's 12b rad 2 over 6a squared. And then I have this 12 over 6 I can reduce. 6 goes into 12 twice and into itself once. So 2b rad 2 over a squared. Okay. The next one, let's see if I can add a couple pages here. We're going to do another one that I'd like you guys to give a try on your own the best you can. So that one is 9x squared y over 32z to the third power, the square root of that whole thing. So see if you can simplify it on your own using the rules that we've talked about so far. All right, so for this one, again, I'm going to run through it just because some of these, they're a bit different for each type. So first thing we're going to do is split it into the square root of the top and the square root of the denominator. Now I'm going to put this into simplest radical form. So I'm going to break up the top into two radicals, break up the bottom into two radicals. First radical gets my perfect squares, so 9 is a perfect square, as is x squared, and y is not. And there's nothing I can take from it because it's only y to the first. The denominator, I've got a 32. The largest perfect square I can take from 32 is 16. And then I have z to the third, and I want perfect squares are even exponents. So I take the largest even number that comes before 3, which is 2, and z squared times z to the first gives me z to the third. Now if I take the square root of those first radicals, I get 3x times the square root of y over 4z times the square root of 2z. Now the problem is that I have this rad 2z in the denominator, and I'm not allowed to have radicals in the denominator. So I'm going to multiply both the top and the bottom by radical 2z. And that should give us in the numerator 3x times the square root of 2yz. So when they're both under the radical and you're multiplying, you can just multiply everything together under the same radical. Rad 2z times rad 2z is just 2z. So I have 4 times 2 is 8, and z times z is z squared. And I can't reduce the 3 and the 8, or the x and the z squared, and my rad 2yz is in simplest radical form already. Next rule. You can't leave a negative under a radical. And very exciting stuff right here, because we are going to introduce a new concept that until now in math, you just knew that you couldn't have the negative. You didn't want negatives under the radical. But now we're actually going to go into a whole new part of our number system, which is imaginary numbers. By definition, the square root of -1 is equal to I for imaginary numbers. So when we simplify, if I take the square root of -4, let's say, I'm really dividing it up into the square root of -1 times the square root of 4. So we just said by definition, the square root of -1 is I, and we know the square root of 4 is 2. So that leaves me with 2I. And just like with variables, you write the coefficient first, the number first, and then the I. And we usually use like a little cursive I for imaginary numbers. I like to say it, and you can't see me right now, but right now I'm holding out my arms, and I'd say a negative. Anytime you have a negative under the radical, pull it up, it becomes an I. So you pull it out of the radical, and when the negative comes out of the radical, it now becomes an I. So that's one way to remember it as well. So we've got -32 for our next one, the square root of -32. So as soon as you see this negative under the radical, you're going to pull it out, and it becomes an I. Then you're going to break up your 32 into simplest radical form. So the largest perfect square you can take from 32 is 16 times 2. So that gives me 4I rad 2. Just like variables, it would go in between the constant and the radical. These already have radicals on them, so you don't need to do plus or minus for them. So you assume it's just the principal square root or just the positive square root. And another imaginary one, we're taking the square root of -7. So again, you see a negative under the radical, pull it out and make it into an I. And we keep the 7 underneath a radical because there's no perfect square that we can take from it. So it just becomes I rad 7. Next up, we're going to now solve using what we call the square root method. When will you need the square root method? Well, you want to use the square root method if you have an x squared term and a constant, but you don't have an x term. So if you have an x squared and a constant, so just a single number is what constant means, but no x term. Because we always say whenever you have an x squared and an x term, that's when you want to get it equal to 0 and then factor it. This is only if you have an x squared term and another number, but no other variable besides the x squared. And this only works if you have an equal sign, so if it's an equation. The steps to do this are you're going to, one, isolate the x squared. So that's super duper important. You need to get x squared all by itself. Number 2, once you have it isolated, you're going to take the square root of both sides. And then 3, don't forget your plus or minus. Probably the most common mistake is forgetting that plus or minus there. All right, and we're on number 9. So we're going to follow these rules for number 9, which is 5x squared plus 18 equals 3. So first thing we need to do is isolate this x squared. I need to get this x squared by itself. So just like you were solving a regular linear equation, you're going to do addition, subtraction first, and then your division. So we've got 5x squared equals negative 15. Divide both sides by 5. And x squared equals negative 3. Now I've isolated the x squared. I have it all by itself. Once I have that by itself, now I can take the square root of both sides. But whenever I take the square root, I have to remember plus or minus. So now I have a negative under my radical. So also review of our imaginary numbers, pull that negative out and make it into an I. And then we don't have a perfect square we can take from 3, so we're going to leave it as a square root of 3. So we have 2 answers here. X equals positive I rad 3 and x equals negative I rad 3. And that's it. Next, number 10. Got x squared over 25 minus 2 equals negative 12. So to do this, again, the main goal here is to isolate your x squared. You need to get it by itself. So to do that, get rid of anything that's being added or subtracted around it first. We have some like terms here. So x squared over 25 equals negative 10. Since I have a fraction on the left side, I'm going to just make this negative 10 into a fraction by putting it over 1. And that way, now I have a fraction equal to another fraction. I can cross multiply. So that gives me x squared times 1 is x squared equals 25 times negative 10 would be negative 250. So now I have x squared by itself, but I need to now solve for x. So I'm going to take the square root of both sides. Whenever I take the square root, I must remember my plus or minus. So I've got plus or minus, pull out my I. Largest perfect square I can take from 250 is 25. So I get plus or minus 5i rad 10. Okay, and the last one we're going to do today is 8x squared plus 7 equals 5x squared plus 4. So this would be a good one to try on your own. The only part that's different here is that you need to start off by combining your like terms. So combine your like terms and then isolate your x squared and solve. All right, so you're subtracting your 5x squared. So we get 3x squared plus 7 equals 4. Subtract your 7. 3x squared equals negative 3. Divide by 3, and we get x squared equals negative 1. So now we can take the square root of both sides. Remember, whenever you take the square root, don't forget your plus or minus. And then don't forget the definition of the square root of negative 1 is equal to I. So we pull out the square root of -1, and that's all that's there. So this is just plus or minus I. And that's it for us for today. So I hope that all makes sense. If you have any questions at all, please let me know. And hopefully I will see you soon. Pi out.